Let's now take a look at this review problem. If z is a complex number, prove that the absolute value of the real part of z is less than or equal to the modulus of z, and that the absolute value of the imaginary part of z is also less than or equal to the modulus of z. To see why this makes sense, let's first draw the picture. Now, the picture isn't the proof, but at least gives us an idea as to why the theorem is true. So let's take a number z in the complex plane. Then the modulus of z would be the distance from the origin. The real part of z would be the distance along the real axis. And the imaginary part of z would be the distance along the imaginary axis. And clearly the hypotenuse is longer than either of the two legs of this right triangle, and so the absolute value of z, the modulus of z, would be larger than both the magnitudes of the real part of z as well as the magnitude of the imaginary part of z. To prove it, proof, let z be equal to a plus bi. Then the modulus of z is defined to be the square root of a squared plus b squared. Now, the square root of a squared plus b squared is greater than or equal to the square root of a squared plus 0. Square root is an increasing function, and b squared must be greater than 0, and therefore the square root of a squared plus b squared must be greater than or equal to the square root of a squared plus 0. That's equal to the square root of a squared. Now, the square root of a squared is not a. It is the absolute value of a, taking into account the possibility that a might be negative. And a by itself is the the real part of z. And by the same logic, square root of a squared plus b squared is greater than or equal to b squared, square root of b squared, because a squared is greater than 0, or greater than or equal to 0. That is equal to the absolute value of b, which is equal to the absolute value of the imaginary part of z. And therefore, either way, the modulus of z is larger, greater than or equal to both the absolute value of the real part of z and the absolute value of the imaginary part of z, and that is the end of the proof.